And we'll go on to our next speaker just a little bit early, and that will be Emilio.
All right. Can you hear me all right?
It's not super loud.
Let's see. Um, okay, well, thank you for having me here to present a little bit on the Linear Collider facility and the path forward. I'd like to start by thanking the LC Vision community in particular for all the great work and discussions over the past few years and the following individuals for helping with material for this talk and helping to prepare it. So I'll begin by sharing with you a statement that was put together by the America's Linear Collider Committee, saying that they're pleased to see the continued ESG prioritization of a Higgs factory at CERN in the post-Halloumi LHC era. We regret that a linear collider facility was not among the top ESG recommendations, but acknowledge the ESG's strong recommendations to build FCCEE, and we look forward to helping realize this future CERN flagship project. The expertise developed over the years by the linear collider community on physics, detectors, and accelerator technology for a Higgs factory will be important contributions to that effort. Now, on a personal note, I'll say I'm not a member of the America's Linear Collider Committee, but I think this statement, broadly reflects the feeling of the community in the U.S. And so, part of the effort in this presentation was really to mirror this statement in how we think about the future for the linear collider community. So what I'll share with you today is a review of the input that our community prepared for ESPPU, both what LC Vision was and what a linear collider facility at CERN could look like. And then I'll talk a little bit about the path forward and how this work can make some significant contributions towards FCCEE, both on the accelerator and the detector front. So LC Vision was put together by a group of enthusiastic individuals at the LCWS workshop in 2024 in preparation for the ESPPU process. I was really motivated by the fact that linear colliders all share the same scientific goals, so we could formulate a coherent physics program together and really define what energy stages, for example, would be critical for linear colliders. Then moving beyond sort of the idea of an individual technology, but would be really required in terms of a facility with infrastructure that would be compatible with various technologies. The idea here being that as the R&D moves forward, and perhaps you're going to attempt to reach higher energy, you want to be able to switch between technologies. So, of course, this is a question in a broader landscape, but how does a linear collider facility fit into the picture as we know we want to move towards the 10 TeV part-ton center of mass scale? Well, the focus at the moment, of course, is on getting to high precision study of the Higgs, but thinking of how linear colliders could provide a pathway to that high energy frontier was part of the discussion for the LC Vision community. A lot of input was prepared for ESPPU, really thinking of it as an umbrella organization that can, as I mentioned, describe the full physics case that's needed for a Higgs factory and the longer term vision, along with the details for a linear collider facility at CERN, with many different options for technologies and upgrades, providing more detailed input as well. So in considering what is needed for a linear collider, really the community focused on a physics-first approach, looking in particular at being able to study the properties of the Higgs, its couplings to other particles, measuring the width to the percent level, followed by a program which would go up in energy, so starting in the range of 250 GeV center of mass, and then moving up into the range of 550 GeV, Really, the target here being to get a good measurement of the Higgs self-coupling, so pushing into the sort of 10% range for that. Ultimately, though, aiming to go higher in energy for the ability to measure additional couplings, and in particular, push the accuracy of the self-coupling down into the few percent range. Of course, a lot of additional physics can be done with a linear collider facility, for example, beam dump experiments, etc. So this was considered as well. And I think a point of pride for the community was having projections that were supported by really detailed and good studies of detector performance for these kinds of facilities. So I'll talk a little bit about that more in the presentation. Okay, so for the facility itself at CERN, really, there were two scenarios that were considered as a baseline for the linear collider facility. The first one was CLIC as a baseline starting at 380 GeV center of mass and then upgrading to 1.5 TeV, but additional running scenarios are also considered in that submission. I'll talk a little bit more about the actual approach to CLIC in a moment, but the other one was a linear collider facility based off of superconducting RF technology with an initial running scenario of 250 GeV center of mass and an upgrade to 550 GeV center of mass with a couple of other points considered as well in the submission. So just a brief kind of intro to CLIC. So CLIC stands for the Compact Linear Collider. It's a two-beam accelerator scheme where there's a drive beam, which very efficiently produces a higher frequency RF pulse, and then that accelerates the main electron and positron beam. This is a scheme that has been studied in great detail over the past couple of decades, reaching a CDR status in 2012 with a focus on getting up to 3 TeV, and an updated project implementation plan in 2018, which focused on 380 GeV as a first step. Given what we now know about the Higgs boson, and what the community felt like was the important first steps for this facility, what was submitted to ESPPU was a machine that started at 380 GeV with an upgrade option up to 1.5 TeV. And an important part of that was also discussing the possibility of being able to do two interaction regions with two detectors that would be fed by the beam at a repetition rate of 100 Hertz. The other option that was considered as a baseline was a modified version of the International Linear Collider for the available community at the CERN site. ILC, of course, is a concept that is being considered in Japan for operation at 250 GeV center of mass. Some of the key differences that should be noted for the submission that went into the European strategy is that kind of boosting up the first upgrade to 550 GeV center of mass was settled on for LC at CERN. In addition, there was consideration of increasing the repetition rate from 5 to 10 Hertz in order to increase the luminosity of the facility. And again, similar to the CLIC submission to ESPPU, it was assumed that this would be a facility that would serve two detectors with two independent beam delivery systems. The kind of siting and civil engineering studies were largely modified from and updated with the knowledge of the civil engineering studies that have been done for CLIC, and a full cost estimate was submitted for ESPPU. So in addition to considering kind of these first stages in running for the linear collider facility, the community had a lot of discussion about what would be the longer term viability of such a facility and what physics could be done. And part of this was considering how could we integrate technology upgrades in order to increase the energy reach of the LCF as time goes on. And so there are two kind of scenarios that were considered. The first was to have a possible luminosity upgrade after 5 years of operation, followed by a technology upgrade in order to go higher in energy. And here you could consider a variety of options. For example, improving the performance of the SRF cavity, perhaps by changing material of the cavity, switching to a normal conducting technology, or even possibly a Wakefield accelerator. The other option that was considered was waiting until the operation at 550 GeV center of mass had completed to then do a more significant jump in energy. And for example, aim to get into the 1 to 3 TeV range without needing to increase the footprint of the overall facility. So the assumption was that something would be available on the range of 20 to up to 33.5 kilometers, and what could be done. Unfortunately, I don't really have the time today to talk through all of those inputs, but as I mentioned, really the following options were considered: an advanced superconducting RF technology, cryogenic copper cavities, warm copper cavities, and Wakefield acceleration. And then there were also some interesting discussions about changing really the mode of operation for the linear collider, moving from electron-positron collisions with a single use of the beam at the collision point to perhaps including an energy recovery LINEC. There was also consideration for doing photon collisions, as well as I mentioned earlier, a significant amount of discussion regarding beyond collider opportunities at the facility. So again, these were reviewed in detail, and these technologies, I should note, of course, were also considered as a standalone facility. So now I'll kind of change direction a little bit and talk about the path forward. Of course, the details of the work that I'm covering mostly has been done so far with linear collider in mind, but we really see a lot of overlap and the possibility for this work to be a direct contribution towards FCCEE. And again, I tried to pick a few examples which could show this connection strongly for both accelerator and detector. And there are many more. So I think the community looks forward to exploring those as well. So I think the first place that I'd like to start with is really thinking about the beam dynamics at the interaction point and the machine detector interface itself. There's been quite a bit of work that's been going on recently trying to improve the codes and the simulation tools that we use for modeling collisions at the IP. Many of us are familiar, of course, with guinea pig, but there's been a lot of great work that's been done to test out the WarpX code, which could have additional advantages in terms of both its capturing of the physics as well as its computational capability. And certainly this could be applied towards FCCEE. Thinking of other things related to kind of the interaction region, there's some nice work going on looking at the possibility of using laser collimation to clean up the halo around the electron beam. And this could be something that is very much of interest for FCC as well. And then other kind of technologies that are of interest in that area, improving the ability to develop superconducting magnets for the interaction region, and also thinking of types of diagnostics which would focus on measuring and improving the luminosity, and I provided some links to those. Of course, really all of this has a lot of overlap with what the needs are for FCCEE, and it'd be great to see those applied there as well. FCCEE has a lot of superconducting RF that is needed for the booster and the collider ring. And this has really been a great area of development for the linear collider community. The frequencies so far have been a little bit different when you think about ILC, at least because it is focused at 1.3 gigahertz. But really, I think the moral of the story is that there's been great progress in terms of the performance of these materials based off of understanding how they should be prepared and also what the material chemistry is for optimizing performance. Really big leaps in terms of the achievable quality factor as well as accelerating gradient. A lot of US involvement in this, so it's great to highlight, for example, the groups at Fermilab, Jefferson Lab, and Cornell. Beyond niobium, of course, changing material topology is something that could be very interesting. Niobium 310 holds great promise in terms of getting to higher surface gradients and also the possibility of operating at higher temperatures, so moving beyond 2K and getting into the 4K range. A lot of great work that's going on here in the US community. And I'll note that even FCC recognizes that if niobium 310 makes enough progress, for example, for their 800 megahertz cavities, this could be adopted. With time, we could think of even more exotic materials. There's been a lot of work that's been done in terms of high temperature superconductors, in particular with enthusiasm for magnets for fusion, but it turns out these could be some very good materials for RF applications as well, going up even to the range of 80 Kelvin operation, which might be great for couplers going into SRF cavities, as well as the cavities themselves. And there's some good work going on between the US and Europe in this area. On the cavity development front for normal conducting accelerators, I'll highlight one example where we've been looking at the possibility of using cryogenic copper technology for injector linacs. And there was a study done and presented at FCC Week in 2024, looking at this as an option for the FCC injector linac, with the option of either reducing the length, which might be very interesting in terms of fitting it on the CERN site, or reducing the RF power requirements, which could alleviate some of the cost of building out the RF system for that accelerator. That work is proceeding at the level of structure tests that will be happening at Argonne, for example, in 2026. And then there's a plan to test a cryogenic copper linac in a cryomodule through a project that is now being led by the European synchrotron, which will really demonstrate the ability to do, for example, the alignment that is needed while achieving the gradient and performance that could be interesting for these types of injector linacs. I'll also note RF sources is a great area of need for FCCEE. There's an extremely large number of sources in the hundreds that are needed for the ring that are CW, and also about 100 sources that are pulsed for the injector linac. Overall, we're talking about 100 megawatts of RF power that needs to be delivered to compensate for the synchrotron radiation. And RF source development has been a real area of in development for the linear collider community, both for normal and superconducting accelerators, which of course FCCEE has both. The present concepts for example, the CW source for FCCEE are at kind of the early stage and need to be transitioned into prototypes and built and tested. And there's some really nice synergy, for example, work that is being funded by the DOE Office of High Energy Physics under the Accelerator Stewardship Program now. Of course, there are leaders in terms of producing high power RF on both sides of the Atlantic. You can think of peak power sources at LCLS or PSI as being a good match to the injector linac at FCCEE. And there's been a lot of work done in recent years thinking of concepts that could improve the overall efficiency of those sources. So definitely some ways that the US could contribute there. So I hope, at least on the accelerator side, I showed you that the technologies for linear and circular have a lot of overlap, and this is something where our community could make contributions to FCCEE. In the interest of time, I'll keep going. And then just a few brief words also on the detector concept side. So there are some significant overlaps and then differences between linear collider detectors and FCC. The energy range that is being considered for FCC spans a fairly wide spectrum, so that needs to be considered in updating these types of designs. There's also significant difference in terms of the fact that there are no bunch trains in FCC. It's a continuous operation in terms of collisions spaced at every 20 nanoseconds. So that's another significant difference for the collider itself. No power pulsing, a lot more data coming out also from the higher luminosity. And so there are differences that are needed in terms of the material budget and cooling budget for the detector itself. But when you look at the collider, I'm sorry, the detector concepts for linear collider and FCC, you'll see that, okay, depending on which detector you're talking about, there is, of course, a lot of overlap between them, similarities in terms of the vertex, options for trackers, the calorimeters, etc. And these are things that the community has jumped on and is looking at very seriously. Uh, I'll give one example for the time projection chamber, the TPC for ILD. For the last couple of years, Daniel Jentz has been leading a group that's been looking at how this could be applied to FCCEE and how do you deal with the challenge that comes with the very large number of bunch crossings that would build up before the electrons have time to drift in the chamber. The community is really thinking about how our work can be applied to new detector concepts for FCC. And then another area that I think in particular is worth highlighting because HFCC has put some support into is maps, in particular for the vertex of the detectors at FCC would be very applicable. And there's two programs that are funded. One, which is a group led out of SLAC, but covering many universities, and one that is also out of Fermilab, and you can see here your partners as well. So really broad engagement across the US in this area. So, the detector community for linear colliders is very strong. They're designs that have really been very well simulated, thought out very carefully, and we really understand the physics potential of those machines. Now, with new emerging technologies in the detector community, it's likely that we can improve on those designs and apply that knowledge to the detectors at FCC-EE. And I think the community is looking forward to making contributions there. And revisiting what can be done in terms of physics goals reach at FCC. In particular, getting to the point where there's, full simulations and designs for those so that the community can move forward with building them. Of course, there's key differences and questions to look into, but that's why we need the expertise of the community. And I guess I'll finish with, again, quoting the ALCC statement, the expertise developed over the years by the linear collider community on physics, detectors, and accelerator technology, will really be important contributions to that effort in, realizing the FCC. And with that, I think I'm out of time, so I'll take any questions.
Thanks very much, Emilio. I'm not seeing any questions in the live document, so I just invite anyone who wants to raise their hand or put any comments in the chat. Looks like none right now. So thank you again, Emilio.